Okay, welcome to this session on hands-on with Project Rediscover, generatively designing Autodesk Toronto's office. My name's Cian Wormsley. I'm a platform architect in Autodesk Research based in Switzerland. You can find me on social media, usually via Cian W, either on Twitter or LinkedIn. And I also have a blog at cianw.com where I post information on the sort of projects that I work on. So a little bit about me. I've been with Autodesk since 1995, which you're probably thinking is impossible, but I was part of some secret breeding experiment or something back in the. But no, anyway, so I've been with Autodesk for a long time. The first few years, 17 years at Autodesk, I was in our developer network team with a variety of roles on the technical side and then on doing some management activities as well. I switched across into the AutoCAD team in 2012 and was a software architect on our AutoCAD-based verticals for some time before moving into research about 4 years ago. And since joining research, I've been involved mainly in projects around integrating IoT data with BIM to create digital twins, such as Dasher, and then also generative design projects using Dynamo and now Refinery. So today we're going to talk about the generative design side of things. I've also moved around quite a bit over the years. I started in the UK, hence the accent. Moved to Switzerland in '98, then to the Bay Area in California in 2000, and then in 2003 to Bangalore, India, and then back to Switzerland again in 2006. So in spite of me being around for a long time, I feel like I've had lots of different jobs and in lots of different places. And since 2006, I've been writing a blog, which I mentioned earlier at cianw.com. You can get to it that way; it's the easiest, and it's called Through the Interface. I started it focused on developing AutoCAD.net plugins, if you like. That's where I started with that. But it's kind of evolved as my interests have evolved and my career has evolved. So I'm quite glad I didn't call it the AutoCAD developer blog. That would have been a bit of a bummer. But anyway, so what we're going to talk about today, we're going to talk about a project that I've had the privilege of being involved in, but I was only one person involved in it, and to some degree in quite a sort of limited way. So first thing we're going to do is talk about the other people in the team who were involved in this project. We're going to talk about Project Discover, which was the original project where we generatively designed the office, and then we'll talk about Project Rediscover, which is where I came in, where we took the work that had been done and created something that we could share more publicly with people. Okay, and then within Project Rediscover, we're going to talk about the elements of it, particularly the geometry system and the evaluation system. Did any of you have a chance to see Lorenzo Villaggi's class this morning on the geometry system? Okay, so I didn't, so I don't really know what he talked about. I'm sure it went into a lot more detail than I'll be going into today, and I for sure can't hope to do justice to it, but I'll explain specifically how the Project Discover and Rediscover geometry systems work. And then we'll talk a bit about a package that we created to help create Project Rediscover, which is a space analysis package for Dynamo and how that can be helpful to you. And then we'll talk about how it can work with Refinery. Okay? So firstly, the team who really did the Project Discover are the Living, based in New York. So I have the privilege of working with these guys from time to time. I've already mentioned Lorenzo. You'll also see Ray here, and perhaps David as well. But yeah, very talented group of people. Clearly, they've been behind a lot of the generative design efforts that you'll see at Autodesk, including the Airbus factory layout project that you'll have seen on main stage this week. So they've been doing really, really cool stuff. Now, on Project Rediscover, it's really been 3 of us working on it. So again, I've had the privilege of working with these 2 gentlemen based in Toronto, Simon Breslav, and Rhys Goldstein. Both of them are principal research scientists. So if you want to understand a bit how the work kind of split up, Rhys is the core simulation guy who's really focused on a lot of the core algorithms in the space analysis package that we'll talk about a bit later. Simon was involved in a lot of the Dynamo work, and then I talk about what they did. So that's kind of... So Project Discover. This is probably a video that's familiar to everybody. I'll actually stand over here so I can look at it. But this is, just sort of an introduction to the Project Discover project. In terms of the way that this system worked, we had a number of constraints that came in terms of the layout of the building, the number of meeting rooms we needed. We wanted to evaluate 6 different metrics to understand how well each design worked. So we had things like adjacency and work style that to some degree took into account what our employees wanted from a workspace. Then we had the traditional kind of generative design process where you generate a design, you evaluate it, and then you evolve over time, over generations. So the geometry system that was created, we'll talk about in a lot more detail shortly, and talk about how you can understand it based on the dynamo graph that we've published. But essentially, the concept is around splitting a space up into neighborhoods, with variable sort of angled dividers between them, and then each neighborhood would be split into amenities and desk areas. And then, of course, no generative design presentation is complete without showing lots of different variations being created. The different goals in terms of evaluation, we'll be talking about how you can do this yourself with the space analysis package. Here, for work style preference, we took into account things like daylight and acoustic levels. And buzz, which is an interesting one, which is around understanding the paths through the office and aggregating them to create a congestion map, if you like. But in this case, congestion being a good thing because you want people to bump into each other and to have discussions. And then productivity it's kind of perhaps at odds a little bit with buzz because you want people to be productive and not just be disturbed all the time. And then daylight, of course, is obvious, trying to maximize the amount of natural light in the office. Where conversely, views to outside, where people can see a window from their desk and not go stir crazy. Okay, so then of course, all these different options get evolved, and we get thousands of design options. And it's very important with a generative design to have an exploration interface, because clearly we're talking about multi-objective optimization. So what may be good in terms of one metric may not work well in others, and then there's always going to be trade-offs. So the exploration of the design space and providing tools to the designer to navigate this space are very important. Okay, and then of course there's usually a selection process where you go through and select some of these designs to review with stakeholders, and then finally sort of evaluate them and evolve the final one. Now, I don't know whether to talk about, well no, I'll actually move on from this. I was going to sort of wrap this up at this stage. So this is the space from the outside, the office that we have in Toronto. Has anybody visited it? Can I see? Yes, of course Russell has, and a few other people as well. Okay, good. And we're on, I think, two and a half floors or 3 floors in this building. It's a fantastic location. It's at there's a major metro line that runs through there with an exit where people just come up the escalator. I think to the tune of 10,000 people a day go past the Autodesk office and can see all these robots and things working away, which is pretty cool. Now the space itself. Here's I'm going to show a few images of the space to give you a sense of how it was. This is an interesting one. I like this. Any guesses as to what this is on the wall there? It's paint. Very good. Who said that? All right. No, so it's actually the results of the daylight analysis have been painted on the walls. So just to sort of, it's kind of a digital physical thing, which is kind of cool. I thought that was quite interesting. This is the main research area. So, actually you can see Simon, he shows up in a few of these images. I don't think he actually ever works like that, but there you go. And then we have a number, so typically we have the interns down here, and then the full-time researchers have closed offices around the top, as you can see from another angle there. And this is I like this because you can start to see some of the strange angles that have come into play in terms of the layout of the space. And I think we wanted to do something perhaps that was a little provocative and didn't have so many right angles, because in a sense it's nice that it looks like it was generatively designed. When we asked the people who constructed it, how was it different from a typical job? I mean, of course, they were like, yeah, it took a lot longer, it was more complicated because there were no right angles anywhere. So, but you can also measure constructibility and the overhead that's associated with that and minimize that as well. So there's or maximize the constructibility, whichever, you know what I'm saying. All right, so this is one of the more traditional kind of office layouts that we, areas that we have. I'm guessing that's the sketchbook team based on the icon on the wall. So that was Project Rediscover. I mean, anecdotally, people are very happy about the space. We do need to do some sort of post-occupancy evaluation and sort of try and loop that back to understand whether all this effort actually has created an office that's better than the one we had before. But that's certainly work that will happen at some point and is ongoing. So my role in this, mine and Simon and Reese's role in this whole project was to take the work that the Living had done originally related to this, and given that we now have tools that are capable of doing that same workflow, from an Autodesk perspective, create something that we can share publicly. Now, we launched this, I think the first version of this graph was launched at AU London in June. Now, I will say that the goals for that first version were really around just getting something out there that people could use. It was not around getting something out there that people could understand, all right? So today, it's more about getting something in your hands that you can explore and play with and really make sense of, because it was a little bit scary. People would download it, open it, and run away or start crying. So this one, we put a fair amount of effort into sort of documenting the workflow, putting in place some nodes that make it just easier to explore and understand. And really what I want to communicate in this class is what you need to do to sort of get to grips with it and make sense of it without being intimidated. So yes, so that's where you can download it from, autode.sk/mars-graph. It's available now, and we'll take a look at it actually. Let's load it up and see what it does. Okay. Oh, I should have loaded it before really, but anyway, we can talk while it loads. So in my case, I'm just going to load it inside Dynamo Sandbox because I think I heard this the other day. Somebody said, because I'm a geek. I think that was Jacob that said that, Jacob Small. Of course, it works just as well inside Dynamo for Revit, but just for the sake of not having to wait for Revit to load it as well, I'm just loading it separately in Dynamo for Sandbox, or Dynamo Sandbox. So we're going to load the graph, the overall graph. What I'll do to start with is run it just so that you can see that it does run. I think that's the first thing to do. It typically takes about 40 seconds to run at this stage on most of the systems that I've tested it on, which is tolerable. Well, we'll see whether it takes 40 seconds to load on top of that first. There we go. So this is the graph. You can see at a high level. I'll very quickly go ahead and click run. So you can see the overall, maybe I can talk about the different areas. We have these are the inputs. We'll talk more about understanding what those are. These sort of green areas are really around sort of processing of the inputs and the data as it flows through. The blue nodes are around display. So these are the things that display, the nodes that display all the metrics at the end, but we added in a bunch of nodes down here that can show the results of different phases, different categories, so that you can see them individually. So there you go, it's completed now. These kind of peach-colored nodes or categories are around the metrics, the sort of evaluation of the various goals. All right, so that's the graph. I'm going to go straight in down here and turn off the preview here. All right, so we don't see anything anymore, which of course is not very useful, but I will go through here. This is what we've done now is essentially create a divide between the geometry system and the evaluation system. So what we can do now is if we freeze this node, then everything down from the geometry system essentially gets hidden and doesn't get evaluated, which means that we can then start to play around with the geometry system and make sense of that without having to wait 40 seconds each time for it to complete. So let's do that. Let's go and freeze this. Okay, and then what I can do then is switch this to automatic. All right. And what we'll do is, so we've got these various steps, right, where we can show, it sort of highlights how things work. So let's start by right-clicking that and saying preview. Oh, actually, do I want to show that one? Well, we can do. This is the actual boundary itself, but those are the windows, if you like. This one we can turn off. So that's the overall boundary. Now this is just a hard-coded boundary. We then have a number of regions that are also hard-coded. These could be loaded in from file, but essentially you have two regions. You have a rectangle here and an L shape here. And then from there, we can sort of go through and take a look at how this breaks up in terms of spines, a central split between each of the neighborhoods. But at this point, I think I'll go back across here and show it inside the presentation because it might just be a bit clearer. But that's how you can go through and take a look at it inside the graph. I've just captured these images and put them inside the slide, so it's a bit easier to follow. So here's the boundary. We've kind of hard-coded the limits of the boundary, but as I said, we could load it from an SAT, we could be bringing it in directly from Revit. We've split it into these two regions, again hard-coded. We have spines going through the regions, dividing each of them, and from there, and it's these spines that help define the neighborhoods in the spaces. So, and this is where things get interesting. So what the way it works is we have as many neighborhoods as we choose to put into this space are then kind of evenly distributed along this spine. So these are also kind of fixed locations, unless we were to add, if we added another neighborhood, things would just get squeezed in a bit more. But these are fairly fixed. These are not going to be varied based on the inputs that come in. So they're spread evenly along the spines. What we do then is calculate some centers for our neighborhoods relative to those original neighborhood points. So these are the orange points you can see there. Now these are defined relative to the spine points, and we use two sets of inputs. So we have three sets of inputs that come into the graph. Two of these are used to define the center points of the neighborhoods relative to the spine points. So you can see there's kind of these spine inputs and these perp spine inputs. Now the spine inputs just say how far the orange dot should be from the black dot along the spine, and the perp spine inputs define how far the dot will be, perpendicular to the spine. So it's pretty simple. It's kind of like an X and Y offset relative to the spine, okay? And actually at this point, it might be kind of interesting to go back across to the graph and you can see how those vary. So here, for example, let's go straight to the neighborhood points, preview them, and then we can go to the inputs. And because we've put things kind of in automatic mode, oops, all right, we can hopefully kind of tweak these inputs. Let's start with the top one. So this is going to, watch this dot here, okay? That's the one to watch. If we click this across, there you go, it moved. And we can go even further. So this is the relative point along that spine. And then if we do the same thing on the perp spine, if we click across, you'll see that it drops down below it. Okay, so that's how those input parameters work effectively. All right. Now, once we have those neighborhood centers, so we're hiding the rest of the stuff now, we're just focusing on those, the centers of the neighborhoods. The next step is to essentially create a Voronoi pattern with those neighborhoods as the center point, okay? Anybody out there have worked with Voronois before? Okay, all right, so, so we're not gonna talk much about it, but you can search it. It's a fairly common technique that's used in computational design. There's plenty of information on Wikipedia about it. I think it's based originally on cellular automata or something like that. I think that's the kind of the roots of it. And so this pattern is then based on these neighborhood centers. And then we can essentially, let's hide the centers, and then we can, basically we trim the Voronoi by the pattern to get our neighborhoods. So that's how we create the neighborhoods. So it's fairly straightforward. Everybody with me so far? Okay? Okay, good. So we now have our neighborhoods. Then we split the neighborhoods, pretty simple. We just sort of put a line. Now well, I say it's simple, but there is a bit more to it than that. We have to choose a side. Everybody has to choose a side. And then we can go a fixed distance in from that particular side is where we put the split. Now, the way it's going to work is that wherever this fixed area is, that's where our amenity block is going to be. And then the other side of the neighborhood is going to be filled with desks. Okay, that's sort of fairly simple. So we split the neighborhoods. It's a fixed distance from one edge, and which edge it is decided by the last set of inputs. So I said there were 3 sets. This third set is what decides which side the amenities block is essentially going to be on. All right. And then we assign the amenities. So the block's placed on the edge at a fixed distance from the edge. Yeah, so, and then we're essentially taking the outer space of it and just offsetting inwards to define the amenities block. And then we also, we fill the areas, of course, but then we choose the entrances to the amenities block to be in the center near the spine, so inwards to the neighborhood. So why is this important? Well, the center of the entrance to the amenity is going to be important to us later when we start to evaluate the adjacency of people's desks to the amenity blocks that they need to go to. Okay, so that's important because you're going to do some shortest path calculations from the desks to the amenities block to say, well, how close is your nearest amenities? Okay, and then of course we just go ahead and assign desks. We use double rows, filling the space that's left, flowing them around any structural columns, of course, that are in that space. Okay. Right, so that's the geometry system. Does anybody have any questions about how the geometry system works? It was all super clear, wasn't it? Great. So how do we then evaluate each of these designs to decide how well they perform or how suitable they are for our needs? These are the original goals that are that were in the Project Discover paper, the original paper. And I think that we basically used more or less the same names. I think we ended up changing interconnectivity to buzz. I think that's the only thing that's really changed. Otherwise, they're pretty obvious. So, distraction. Oops. Right. So this is, we calculate this based on the proximity to other desks, because essentially we want to make sure that people don't have too many visual distractions from people who are around, and we also then take into account the congestion in the office as well, because people are going to get distracted by congestion. So this is where distraction is slightly at odds with the buzz metric. So we want to encourage, increase buzz without increasing distraction. So adjacency and buzz, we calculate these. It's pretty straightforward. We just do a shortest path analysis between the desks and a number of landmark locations. and the amenity blocks as well, as I mentioned before. So the landmark locations, you can kind of see them. I think there's one there, and I think there's a third one somewhere here anyway. I forget where it is. But basically these landmark locations are the entrances to the, where the lifts open up, the elevators open up. So this was kind of one of the calculations that get done. All the black lines are the paths, the shortest paths between the desks and those locations. So we calculate these using the space analysis package, which I'll talk about in a little bit. Now, essentially what we do for adjacency is just take the average length of all these paths to understand, to make sure that we minimize that. So we want to reduce that to a maximum, of course, via the optimization process. Buzz is what we do is we create a congestion map based on all those individual paths. They contribute to a congestion map. So the more common routes where we have paths, where regularly lots of people at different desks are going to be following the same path, that weight, gets increased, and we can display it like that. So I think this is kind of cool. These visualizations, especially when you start to animate them. I kind of want to do a project where we actually order the images based on some animation that we want to create, rather than I shouldn't really. I think we could have some fun with this. So the next one is views to outside. So here we create a visibility map from the window points across all the floor locations. So essentially, you can decide from a particular desk whether you can see a window. That's ultimately what we want to do. And we also use the space analysis package for this. So yes, we calculate the visibility from each desk. Essentially, the visibility of going from the window to a desk is equivalent to from a desk to a window. So that's kind of how we do it. And then in the visualization, we draw a line from the desk to their closest window point that they can see. Okay, work style is the next one. And this is an interesting one because this is actually based on employee survey data. So all the employees got asked, how would you like to work? Who do you need to work with? How do you like to work? Do you like an open space? Do you like an office? Do you like daylight? Do you like to be in the dark because you're a coder? Who do you need to work with, et cetera, et cetera. So all that gets taken care of. Inside this graph, of course, we haven't shared that data because that would be a bit strange and probably illegal. So we've just put in some synthetic data that gives you a sense of how it works. Okay. The colors inside the visualization reflect the degree that each neighborhood matches the work style preferences of the teams that are allocated to that space. Okay, so that's, I forget how exactly the allocation works. I think it's based on size. We kind of pack in the teams based on, the space available in these neighborhoods. But then, of course, this metric, the work style metric, is where we assess whether the teams that are in those spaces are going to be happy with the allocation. So daylight. Now this is an interesting one. When we released the V1, we had a very home-rolled approach, if you like, for this, where we just kind of established some sun points and did some ray casting through the windows to understand how it would work. But it was actually kind of slow and expensive. And then we realized that we could use the solar analysis package that is kind of a little bit old now, maybe. I mean, it hasn't been updated in a while, but it works really well. And it's based on the original Ecotect engine. So it's much more efficient, and we found that it really does the job. So that's kind of how we do the daylight analysis at this stage. And we kind of calculate and display a year's worth of data, which is how it kind of gets aggregated into this one daylight map. Okay, so space analysis, which is this package that we created. Essentially, it's a Dynamo package that simplifies 3 different analysis workflows. And they all use the same core data structures, which is, so it's 2D based. The first thing that we wanted to tackle was pathfinding. The second was visibility. And then the third, that we haven't actually used in this graph, I don't think, as yet, is acoustics. So this is all the stuff that Reese does. He sort of, anyway, comes up with these crazy ideas and manages to implement them. Now, the original implementation is in C++, and we really did something that was optimized for generative design. It's 2D only. It has a certain fixed resolution. We use the same data structures for some degree of commonality and comprehensibility. I guess it's also fair to say that it's not physically accurate, so don't assume that the acoustics analysis is something that you can rely on in terms of real-world physics, etc. We haven't calibrated it. Anecdotally, we've found some interesting results that kind of suggest that it's pretty good, but the intention is not to do something or create something that can be used professionally to do a proper acoustics analysis. It's just directional. You want to say whether one design performs better than another. You don't necessarily need to know the precise values of the analysis. Okay? That's all the case with all of these. Even with the shortest path stuff, it doesn't really matter whether the paths are really smooth, etc., etc. It doesn't matter so much as long as each of them are as jagged as the other ones. So it's all directional. So a core data structure that we use, as I mentioned, for this is the space lattice, and it's used for all these three types of analysis. And it's essentially a diagrid, so it's squares with diagonals across them. Within Dynamo, you sort of open up the nodes inside Dynamo, and you'll see these kind of high-level namespaces. You have acoustics, you have core, pathfinding, utils, and visibility. Acoustics, pathfinding, and visibility are the three types of analysis, of course. And then it's inside core that you'll find the space lattice. Some important concepts related to the space lattice. If you're having trouble understanding why something isn't working, you can just turn on the edges, and you'll very quickly see these lines here, and you can make sense of whether you need to do something like change the resolution, because the resolution is going to make a difference. If you have a very fine-grained resolution, it's going to be more accurate, but it's going to take a lot longer to evaluate. Whereas if you've got a lot coarser resolution, you may get yourself in trouble because you won't be able to, there'll be gaps and people won't be able to navigate through spaces that they should be able to. You also need to sometimes call the closest point to method in order to make sure that the point that you're testing for your pathfinding is actually on the grid. Because sometimes, if it isn't, you might get in trouble. So that's another important point to note when you're using the space lattice. So there they are. You can sort of see these. This is within core, you have the space lattice, and these are the methods and properties associated with the space lattice. Okay? And so there you can kind of see, at a very simple level, kind of how this works. We have a certain resolution. This has been added as a barrier, and then we're just doing a shortest path between this point, and it's kind of, that's the route that gets calculated. So you can do shortest point from one point to another, shortest path from one point to another, from one point to many, to many different points, or from many different points to one. In this case, if you're doing one to many, it'll kind of get the nearest of the many points that you choose as destinations. You can also do route smoothing. That's something that we've added as well. If it's important for you to have, we can do iterations of smoothing. Some of you may be wondering about Revit's path of travel feature, which kind of seems similar to this. That is actually much more elaborate and I would say accurate as well. But it isn't available inside Dynamo, at least not in generative design workflows. So for now, we've chosen to go our path. It may make sense at some point to do, we're speaking regularly to the Revit team about what makes most sense longer term for that. Okay, so here we have the sort of how you create a space lattice, sorry, a path field based on the space lattice and an endpoint, or the space lattice and a start point. And then from there, you create a route, based on the path field and the space lattice. That's kind of how you work through it. Visibility. So it's kind of interesting when Reese came and suggested that he could also, do visibility analysis based on this same concepts that he's implemented for pathfinding as well. So there's a few ways that we do visibility. Typically, inside the Mars graph, we use the idea of a view cone, which essentially allows you to limit visibility and calculate only in a certain cone. We have to create a view field based on, the space lattice and a view cone, or the space lattice and a viewpoint. So there we go. And then we have a visibility grid. So you can essentially, so let's take a look at these. So the field of view is created based on viewpoint or view cone. You can have global or local visibility. Typically, you can specify a radius, if you want local visibility. And then in terms of aggregating the results, you can either do union or intersection of multiple view fields together. And then just for visualization purposes, you can map the results to a surface, just as we're showing there. Now, I was really surprised when Reese said he could do acoustics as well as pathfinding and visibility. And essentially, this is in this case, what we're visualizing is a sound system. We have multiple sound sources based, with the same frequency. It's interesting because there's this kind of strange interference pattern between the two, and we thought this was kind of anomalous when we looked at it. But then we started to research a bit more, and we found some blog posts that sort of physically tested this and showed that you very do often, when you have sound sources with the same frequency, you do kind of get this dead zone, and not necessarily, and it tends to be, I think there's two of them actually. So you can see here, it's very interesting. Here as well, you kind of have two of them. But it is something that is played out in reality, so it's quite interesting to find out. So the nodes that we used are very analogous to the ones for visibility. As I said, we have sound system. If you have multiple sources of the same frequency, you can vary the intensity locally and globally. We have different volumes. Now, because so when you set the nodes up, you specify a particular desired wavelength, it may actually vary. The one that gets used may be different from the one that you choose. So you can also then query for the nodes to ask what those should be. So here we create a sound system based on sound points, and you can also choose intensities as well. And then a sound field by the space lattice and sound point, or space lattice and sound system. And that's where we query the wavelength. Okay, and then this is very similar to a visibility grid. We have an audibility grid, which is essentially analogous, as I said. All right, so that's space analysis. Install it via the Dynamo package manager. You can just search for it there. I think it's had about 1,000 downloads so far, which we're really happy with, probably more by now. If you want to explore the samples that, effectively, all these samples are available underneath this folder. It's sometimes a little quirky, but if you go under App Data, you should be able to find it under Dynamo, and then Dynamo Revit or Dynamo Core, and then whichever version you have installed. And there's an extra folder basically underneath the Dynamo package folder, which has a load of DYN files that you can load in and play around with. So please give us feedback via the Dynamo BIM forum. We'd be happy to hear from you. You can also contact me via my blog or social media, etc. We are planning to release this via open source at some point. So one of the reasons Reese implemented this is that he also does some discrete event simulation work. We have an open source project called SciDevs. He'd very much like to integrate that with SciDevs as well, because it's important. It's an important piece of functionality that's relevant there too. So ideally, we'll get this open sourced in due course. So a quick shout out in terms of other things that are worth looking at. How are we doing for time? All right, pretty good. So the refinery toolkits, now there is some overlap in terms of what we've done from in our research perspective and what the Dynamo team, the development that's been done through them and through some external contractors to create the refinery toolkits. So we essentially have inside the refinery toolkit some capability of doing space planning and massing, and there is a bit of overlap with space analysis. You know, we had selfish reasons to implement the tool in the way that we've done. We're also, as we're talking to the Revit team, we're also talking to the Dynamo and refinery teams about what the best path is going forward. Does it make sense to merge things, rationalize things together? So these are already open source because they're part of the Dynamo DS repository. If you're interested in contributing, please do. We're very happy to hear from you, as well as getting feedback on them as well. So there's a beta release. So it isn't yet available in the Dynamo Package Manager. You can essentially go to this GitHub link, and you'll find that there's a beta release posted there that you can download. Okay, so it's still quite early in that sense. Okay, so rediscover and refinery. How many of you have used refinery already? Okay, so refinery is essentially an optimization engine that you use with Dynamo graphs. And when we take the Mars graph, what we do is we publish it locally on the system, and then if you want to create a new study inside the refinery UI, you then have to go through, and for each of the 6 goals, you can decide whether you need to minimize or maximize them. So we've handily sort of explained when they should be minimized. For some reason, we forgot to put a maximize on work style, but anyway, it doesn't matter. It should be clear what you need to do there. You can also constrain the outputs if you want to have certain limited, only look at certain limited results. But then the optimization process typically will specify a population size, the number of generations that are going to get passed through, and then a random seed. You don't really need to worry about this, but just bear in mind that if you do multiple studies with the same seed and the same population of generations, you're going to get the same results each time. So if you want to shake things up a bit, you may want to put in a different random seed. It's just the way, it's a pseudo-random number generator, uses the seed in order to change it. Now, the refinery does work well with this version. We found with the first version that we posted, because we added some sort of parallelization nodes in there where we had a special flag to turn them on or off. If you asked to do some parallel processing in Python, it sometimes caused some issues with the refinery, just because of the way the memory is used, etc. Nowadays, I've actually found in the latest version, there is no real benefit to turning this on, so we've just put the default to false, just leave it like that, and it'll work just fine with refinery. So there's nothing you need to do there. It also works with something called Capture Refinery or Capture Finery. It depends. When I built this, I decided not to put a capital letter in the middle because I wanted to leave it ambiguous, because I figured, well, people can read it however they want. Has anyone tried this tool, Capture Finery? Okay, a few of you. It's kind of fun. I mean, one of the things that we found is that you often want to create presentation graphics based on your refinery studies. So this takes a refinery study and allows you to go through and generate a bunch of graphics and create animated GIFs or GIFs, if you prefer, that you can add, put in presentations. So this is a refinery study that I sort of ran on this system to test. You can see the results. Typically the way it works is that you specify which of the metrics that you want on the x-axis and the y-axis. You can also choose another metric for the size and another metric for the color. So you're essentially mapping 4 dimensions into a 2-dimensional space. Obviously, if we had VR, we could get 5 dimensions in a 3-dimensional space, but that's something that we'll get at some point, I guess. The way it works is, as you hover over items down here in the design grid, they get highlighted up here, and vice versa. If you hover over items in the scatter plot, they get highlighted here if they're visible. And then you can choose one and then open it in Dynamo. And what that does is it transfers the input values for that particular result into Dynamo so you can explore it. You know, you can run it and take a look at it inside Dynamo itself. So this is another run. Capture Refinery, as I sort of mentioned before, this will show the different studies that you have. There's only one there. If you select it, then you can go through and specify some parameters. It's not very it's not very complicated, but it's not very clear either, to be honest with you. But here you specify the indices of the items in the study that you want to run. You can include intermediate results. So typically what it does is it just takes the last, what we call the Hall of Fame inside the refinery study, which is the best results that it's found across all the generations. But if you include the intermediate results, it'll take all the halls of fame that were there at the end of each generation, and so you tend to get more results in there. And then if you want to create the animations, you can specify a name, and you can also do some sorting based on a particular input parameter or output parameter. And so we also did it to an arbitrary level. If you really want to do sorting based on all the different input parameters, you can, but frankly, it doesn't make any sense to do that. Typically, you know, if you sort on the first couple, it really, you know, it's just plenty good enough. So this is the kind of, you know, result that you get. This is from that run that I showed. And I think if we look at this spider graph here, you can see, I think it's the third item there. So I think we've probably sorted it based on distraction, because you can see that it's gradually going from outwards to inwards. And there's 182 different values sorted on that axis. I didn't have any control at a programmatic level on how quickly the animation goes, because there is no, you know, you can then post-process it using a tool and like GIMP or something like that, and then change the delay between each frame. But by default, I think it's only like 10 milliseconds, and you can't really control it. But so that's why it goes quite quickly. But in a sense, it's kind of cool like that. But so that's one type of visualization. But ultimately, you can then go into Dynamo and then adjust the 3D graphics view and turn on different previews and rerun Capture Refinery and get different results. So here's another example where what we're doing is actually combining the congestion map with the desk layout. And showing that kind of in a more of a 3D view. And this one, I think we're sorting, can anybody see which one we're sorting on there? I think that's sorting on buzz, which would make sense. So you can see it's kind of going outwards from here gradually. That it's been sorted based on buzz, all right, as it goes outwards. And so the next one that we did, this one was showing the daylight analysis alongside the views to outside, I think, and this one is sorted on daylight. So here we can see, you know, this is the axis or the metric that's being sorted on. All right. And then I think just for fun, the third one, this was work style preference alongside the sort of paths, shortest path calculations that we did. So you can see it's kind of, I think it's kind of interesting. You can start to, I mean, inside the refinery UI, you can certainly start to see correlations between data and sort of trade-offs and that sort of thing. But this is just another way of seeing that graphically. And you can ultimately turn on whatever you want inside the Dynamo graph to create your visualizations and presentation graphics. Okay, so I mentioned a couple of phases of this project. The first one was just getting it out there so that it's something that worked. This phase has been about getting something out there that is understandable. I think if we do go further with this, the chances are we'll take a look at performance. Just before this class, I did load it inside a tool that was created. I think it was initially created at the Dynamo user group hackathon earlier in the year. A team came up with a Dynamo diagnostic toolkit, and it's still a work in progress. But you know, you can go, you know, you have to compile it from source and everything at the moment. So it's a little bit. Most people won't want to do it, but at some point it'll be available via the Dynamo Package Manager. And this essentially allows you to profile the performance of a Dynamo graph and understand where the performance bottlenecks are, etc. So here, the bigger bubble. So this is the Mars graph. You can kind of map it to what we saw earlier. This is essentially each of the nodes is at the location that it exists in the graph. But these bubbles, the bigger the bubble means the slower the performance, the longer it took to evaluate. And then here, essentially, we're sorting those nodes based on the execution time. So you can start to then dig into these different nodes and understand, should they be working like that or not? Here, for example, is an interesting one. We use space lattice.edges. So we are getting the edges of one of our space lattices, but we're not visualizing it. So maybe that's something we should freeze to stop it from executing. But that's the kind of logic you can use, and it helps you to understand and then tune the performance of your dynamo graphs. Okay. So, does anyone have any questions? Yes, over there. Yes.
I'm guessing it makes it faster, but is it a better way to go? Would you recommend doing that or using regular?
Okay, so I'm going to repeat the question a bit because for the recording, I think it makes sense. I don't know if there's a separate microphone, but anyway, I'll repeat the question. So there's a lot of Python and sort of some custom code in it. Probably makes sense for performance, but is that the best way to go? I don't know. Lorenzo's snuck in the back there, but so we could probably ask him. I think one of the benefits that we had of using Python is that we're able to. It's very transferable between different systems, and of course we're taking some of the original code that the Living created, quite a lot of the original code that the Living created, and we can just drop it into the Dynamo graph and run it like that. Of course, we could have perhaps rebuilt that as a node, but that also adds complexity to the graph as well. So you kind of got, it's complex. You've got complexity either side, whether you want it or not, I think. So in this case, it turned out to be, their code was actually pretty good, so we just went with that. So thanks. And there was a question down here, yeah.
Yes. Were you able to weight the metrics when you're going through the analysis to determine, so maybe buzz is more important to you than seeing a window?
Well, so part of that, you can sort of weight things in terms of deciding when you define the metrics, you can obviously control that inside the graph itself, but then also inside the exploration interface, you can, that's what the tool is there for, is to sort of understand what the trade-offs are. And as a designer, you can say, well, actually, I really don't care as much about this metric than another, so you will focus in on the ones that are more important to you, and the other ones become kind of secondary. Yeah, I think. I'll go over this side and then come back to you. Yeah.
I'm curious, the quantity of desks seems to be directly derived from the geometry of the complex, I guess.
Yeah.
How did you take into consideration the fact that maybe your team doesn't have many people, many desks, or maybe 3 more desks, or?
Good question. I think so you're quite right. I should have repeated the question, but anyway, over there as well. But so the desks seem to just fill the space that you have available. It's not necessarily saying, well, we don't need as many, et cetera, et cetera. So in this case, it was fairly rudimentary. It's exactly what you said. We fill the space with as many desks as we can. Do we need them, or do we need more? Well, of course, we won't fit teams into spaces that don't have enough desks. But yes, we could probably remove desks if we didn't need them, but we haven't, taken that into account. But please do when you create your own version. Yeah.
And you can automate that task. You can make it part of the graph.
Yeah, so all of this, yes, so could we automate it? Yes, there's lots of directions you could take this into, take this in for your own purposes, for sure.
Yeah.
Yes.
Can you take the output of this analysis and export it or use it in Forge?
In Forge, interesting. So question is, can we take the results of this and use it in Forge? Now, ultimately you can create geometry so you can create Revit nodes, Revit elements based on the results. You'll typically, the way it would work is you'd have a set of nodes that push the results into Revit and you freeze them, and then, or they don't load when you do the optimization, but then when you choose a result, you can say, okay, we'll send the results to Revit, and then Revit, obviously from Revit, you can have that inside Forge and access it that way. Or any other geometry format that Dynamo can speak to. I don't know everything about
Because
what's
what I love
possible
is
there.
that, you guys now have that data
Yeah.
applied in a graphic way that you can understand right away,
Yeah.
visualizing that.
Yeah.
So, and I know that when I asked, I think it was yesterday, if Forge can take directly the data from, say, Dynamo, I think you said at that point, no, not yet, but we maybe in the future. But that this way, they can take that images and use it.
Ah, right. So the imagery that we're creating here, I mean, you can definitely do it from Dynamo. So yeah, so you can take the Dynamo, you can create things inside Revit, but I mean, the images, this is kind of more of a presentation tool. I mean, the Capture Refinery images, it's more of a presentation tool. But anyway, maybe we can talk about this offline, and because I do want to come back to the gentleman who had a question before, but. Right.
And then second, of course, it's pretty evident this is very technical and takes some specialized skills that we need to run.
Yeah.
And how do you envision, or is there some type of plan to be able to help the common designer realize functionality?
Fantastic questions. So the first one is around how long it takes to execute a refinery study using the graph. As I mentioned, each design typically takes about 40 seconds to generate, probably less if you sort of don't worry about all the graphics and all that sort of stuff. But you know, it really depends on how big a study you want to do. I mean, the one that I had, which ended up having 180 odd results, it was hours, but not days. So it's like maybe 3 or 4 hours, something like that, on a fairly good system. Over time, of course, we'll probably have the capability, I suspect, maybe one day of running this in the cloud and not tying up your local system, etc. But that's, speculative. Now, on to the second part of the question, which is around the complexity of this and how do we democratize that within design teams and not rely on the priesthood to sort of, do stuff for you. I mean, that's definitely our plan of, and even in what you can start to see within Refinery itself, the evolution of it, there's a publish step where you take your Dynamo graph and you export it to Refinery, and then when you can launch it without ever seeing Dynamo. So you just have the UI, which allows you to sort of specify the parameters for your study without you even knowing that there's a Dynamo graph behind the scenes being executed, right? So that is kind of the first step in that direction, and I think gradually we'll provide some sort of capability where, it's the Dynamo graph is the source code, right? That nobody actually ever kind of sees. It's just an implementation detail. And then the people who are doing the actual sort of design work, yes, they'll load in their constraints and specify the initial conditions for the study, but they shouldn't be exposed to that level of detail. And that's definitely where we're going in terms of raising the level of abstraction and sort of making it easier for people to make use of it, or to have, different roles in the group, but it's not the hardcore technologists who are doing all the studies. Yeah, if that makes sense. Yeah. Any other questions? Wow, we're on time as well. Well, thank you very much. I appreciate it.